Welcome all of you to MCS control room, that means control system classroom. And in the previous classes, what we have discussed about the analogous system. That means there are uh, two systems. One is force voltage analogy and one is force current analogy. For force voltage analogy, we have used the series RLC circuit, and for force current analogy, we have considered the parallel RLC circuits. So uh, basically, this is the systems equivalent values I have written here. This is force voltage and this is force current. A series RLC circuit I have considered, and here also parallel RLC circuit are considered. Now in this lecture, what we will concentrate how to draw a corresponding circuit or network, that is the electrical circuit corresponding to a mechanical system given to you, right? From mechanical system given to you, we have to get the electrical system network. So that is our aim of this class, right? And see, in order to draw the corresponding force voltage or force current analogy, we have to first consider whether this will be series RLC circuit. That means the series combinations. Series combinations means what? Series combinations means KVL. That means what? Concept of loop, right? Just try to understand what I am telling. This is series RLC circuit, and this series RLC circuit in the electrical system corresponds to a force voltage analogy, right? And parallel RLC circuit, when we consider, definitely what we have used the tool, that is KCL, that means the concept of node, right? So here current is the forcing function, here voltage is the forcing functions. So we will consider one example. Already we have developed the mathematical modeling for that in the mathematical modeling of mechanical system classes, that I am taking the cart system, two mass cart system, where one end is rigid and say this is spring K2, this is your C B2, and here a mass is connected, which is M2, friction 0, F2 0. Again this is connected to some spring, say K1, and this is B1, this is M1, F1 is equal to 0 we consider, and force is applied here, right? And displacement of this body, say in this direction x1, and displacement of this body in this direction x2. Now corresponding to that, what we have to do, we have to draw the equivalent electrical circuit, that means the network we have to draw considering these parameters in mind. And there will be the two analogy. Definitely the two circuits will be there. One analogy force current analogy, one is force voltage analogy. And once you draw the force current analogy, we have to consider the node, right? And one concept is that, first of all, you see, when you have written the differential equation corresponding to any mechanical system, there is a mass. So mass d2x dt2, you just consider the term mass, mass d2x dt2, right? So this gives a differential equation, second order differential equations. Similarly to that, we have to consider that, that means any second order differential equations constitutes with the help of mass. So when there will be a number of masses, so in that case there will be either a you see single loop or multiple loop. So that I will discuss in detail now. But I will suggest, first of all, force current analogy, drawing of the force current analogy, that means the force current analogical electrical circuit corresponding to the mechanical circuit is very much easier. How you can get it? That can be obtained with the help of simple this mechanical network. Now this is your mechanical system. From this, if you get the mechanical network, right? So mechanical getting of mechanical network, will directly give you force and current analogical electrical network, right? So how you can get it? See, for getting this force current analogy, first of all we will get the mechanical network. Mechanical network means this is the rigid surface, right? This m1 is connected to some external force F, right? That means you see basically a which one terminal is free and has associated with it motional variable v1. One terminal means this associated with this motional variable, that's x1 is there. That means you see in the previous classes we have discussed about that some v1 variable can be here, right? So, and variable other terminal depends reference with respect to which the motional variable has been actually used has been measured. The free reference terminal with respect to which this measurement of the velocity is considered, right? So how the a mechanical network corresponding to that can be drawn? See, first of all consider this mass m1, right? So m1, here you can write it as so like your mass, so you can write it's like m1, right? So this is one terminal, and one terminal is free. So here you see this is your force, right? So force is applied to this terminal, right? Force is applied here, and once the force is applied, and definitely this is moving in these directions, and you see this k1 and b1, these are the two opposition force giving element. That means they are actually restricting their operations of moving this m1 in this direction. So these two elements will be connected to this terminal. How? This is your k1 and this is your b1. Say this terminal is same as that terminal, this terminal is same as that terminal, right? And they are as it is from this structure, you see these are like parallel structure, right? And here also one mass m2 is connected. One mass here m2 is connected, and other terminal of the mass is connected with the K2 as well as B2, and this K2 and B2 they are again connected, can be like this. K2 and B2. Now see, this is the structure, this is the mechanical network. This force is applied at one end of the mass m1, and this other end of the mass m1 is connected with the parallel combinations of these two. These two are parallel combinations, and these parallel combinations that means this is these two ends will be connected together, and these connections is made with the help of this m2 structure, right? And this m2 is again connected with this is your surface, rigid surface. So these connections, these are the 2 points which are connected, and they are connected like this to give a mechanical network like a structure. And mass is used here as a 2 terminal component, actually either m1 or m2. These two are connected or used as the you see this is the reference 2 terminal component. One terminal again I see is free and associated with this motional variable v1, right? And this is free, with the motional variable v1. This is connected, and other connections is like this. Similarly to this, m2 is connected here. So without having any uh, rule to keep in mind, you just go on drawing this structure like this, that these are parallel structure, these are kind of parallel structure, and the two ends of this uh, uh, this network and this network are connected by a node like structure. So here you will get a node, here you will get a node, right? Now see, I am doing what is known as force current analogy, right? So you see, this is node, this is node. So how many nodes you get? Two nodes. How many nodes you should get? The number of nodes in electrical network corresponding to mechanical network will be equal to the number of mass present, right? So from this structure, the easier way to remember is that just make a mechanical structure like this, or mechanical network is like that. So number one is that number of masses, number of mass equal to number of nodes. Okay, so this is the basic and foremost criteria to draw any force current analogy. Now if this is your network, next is that replace all the elements of the mechanical network by corresponding electrical network. So all the elements to be replaced by electrical elements. So all the elements to be replaced with electrical corresponding to electrical elements. So I will just erase it and put the values of M1, Q1 and B1 in respect to the electrical network values, and F, instead of F we will write it as current I. So what we get? See, this is spin. So K2 current, this is 1 by L. So this will be like this, which value is 1 by L1, L2. I see it. Next, this is B2. B2 means 1 by R, right? So this will be resistance having value 1 by R2. You can say it. Now this is the mass, that means capacitance, C2. We can say it, C2. Next, here two parallel values are there, K1 and B1. K1 means again 1 by L1, and here you see B1. B1 means 1 upon resistance. So we can say it 1 by R1. These L1, R1 are the suffixes basically to denote either represent B1, Q1, A1 or M2, B2, A2 like this. So this is the structure. Again, there will be one M1. M1 means another capacitance, say C1, right? And this force is basically current I. You see, this is the equivalent circuit. And one of the major thing which is to be noted is that there is a third variable, third point. See, number of masses equal to the number of node. So number of masses M1 and M2. This is your node 1 and say node 2, right? And F equivalent to I. All the related variables will be replaced by corresponding resistance, capacitors, and inductance, and so on. And one thing is that means all the variables in the mechanical system by using this force current analogy is replaced here. And third one is that this other end of the mass was the reference, right? This is a two-terminal device. I was talking about the two-terminal device. One is connected to the one end is connected to the motional velocity v, other is connected to the basically ground. So see, these masses are replaced by basically capacitor, and the other end of the capacitors are made grounded. Okay, so these are the two ends which are the capacitors. So number of masses will be replaced by number of capacitors, and the end of the capacitors are grounded. One end is connected to node V1 V2, you can say it. Other end connected to just like capacitors, other ends are connected to ground, right? So this is the way how you can draw the electrical circuit network corresponding to the mechanical circuit by using the force current analogy. And this is much more easier than to get the force voltage corresponding circuit in electrical network. That is why I have discussed it earlier. Now the same mathematical mechanical model we will consider, and we will write how to we will see how to get the force voltage analogy of the system, right? So this is the way. I again repeat: force current analogy, number of masses equal to number of node, and number of masses equal to so there will be two nodes. There will be one node, another node, and the masses are replaced by capacitance, you know, in case of force current analogy, and other end of the capacitance are grounded. That is the first criteria. Next, all the elements to be replaced by electrical corresponding elements, and by using that you can get the force current analogy, right? So next we will go for current voltage analogy. So here, for the same system, we will develop the force voltage analogy. So in the force voltage analogy, what we have done, force voltage analogy for the electrical circuit, we have considered the series RLC circuit. So again, for series RLC circuit, we have used the KVL, Kirchhoff's voltage law, and once the Kirchhoff's voltage law is used, that means you have to consider the loops. So here the main rule for both voltage analogy is that you have to get the number of masses equal to the number of loops. Next thing, all the elements are replaced by electrical elements. So these are the two common rules, right? So step by step we will see what are the different kinds of loops we can consider. That means there are, sorry, this is your M1. So M1 and M2, this will be the two masses here, and we will get the two loops definitely. So maybe this is kind of one loop, and another is kind of a loop. And what is the forcing function here? You see the forcing function is F. So forcing function is F. That means in case of force voltage analogy, what is the forcing functions? That is a voltage source. So we will use a voltage source V, say, right? So this is the connections with the voltage source. And now see, is this K1. K1 means this is 1 by C1, and this is connected with one another B. B means one resistance path is also there, right? And see this can be your M2. M2 is connected to this K1 and K2 and B1 and B2. See here for force voltage analogy, and once you are going to get the KVL, that means the loop, concept of loop. What happens? Concept of loop means there is a common path, you see. So this may be one loop L1, this may be another loop L2, right? So what happens? This is a common path, right? So loop means there may be multiple loops. So multiple loops means there will be common path. That means the common connections is there. Here you see this K1. K1 is connected to M1 and also M2. That means if this is your loop L1 and this is in loop 2, that means the two masses will be having values like L1 and L2. This L1 and L2 will be in the two different loops, right? So that is clear. So M1 and corresponds to L1, and M2 will corresponds to L2. That means we can call it the two different loops. And you see this what happens in case of K1 and B1. K1 and B1 is connected to M1 as well as M2. So definitely K1 and B1, these will be connected here, right? This will be connected here. This is the common path, right? So here we will get the K1. K1 means what? K1 means R1. We will be having one path known as R1, right? And we may write it R1 and B1. B1 means sorry, this K1. K1 means 1 by C1, 1 by C1, and B1 means 1 by R1. B1 means R1. So this is your R1 and this is your 1 by C1, right? Uh, just I will write in bigger version so it will be easier for you to understand. So we will be having two loops because of having two masses or force voltage, and as in the force voltage KVL we are applying. So first of all, the force voltage means this will be your forcing functions, which will be your voltage. Okay, now M1 can be for loop 1. Say for example, this is I can see this is your loop 1, this is your loop 2. So you see this is loop 1. Loop 1 is for M1 and loop 2 is for M2. That means there will be two capacitors. Why? Because two inductors, M corresponding to inductors. So in this loop there will be one inductor, in this loop there will be another inductor. Next thing what you have to see, you see the connections. This is K2 and B2. They are connected to the rigid surface. Okay, and K1 and B1. K1 and B1, K1 is connected to both this M1 and M2. That means K1 is the common path of the two loops, and this B1 also common path between the two loops. And you see for any loop already I have discussed there is a common path. So in this common path there will be two elements. What is this? This is K1. K1 means 1 by C, 1 by C1 I can say it, and this is B1. Say this is R1, right? So this is common to both the loops, this loop and this loop. This is your voltage, no problem. And in this loop now, this is your grounded common path. Now in this loop there will be one mass, that means one inductor. So you can write here one inductor, that is your L1. So this is the first loop. So L1 means M1 is replaced, K1 means 1 by C1 is replaced, and B1 means R1 is replaced, and this is the common path between the two loops. So M2 means another inductor will be there in this loop. So you can use another inductor, say this is L2. Next, this L2 is connected to this K2 and B2. K2 means what? K2 means one capacitor, and B2 means one resistor. So what happens is that you see this is as K2. K2 means 1 by C1. So you can use one capacitance here with the value of 1 by say C2, right? And that part is this is say for example the rigid surface that is grounded like that structure, and one end of the K2 is again connected to this so common path. So here you can use one resistance because this is your B. So this is your R2, right? So this is the structure in terms of force voltage analogy, right? So what you have discussed, number of meshes L1 L2 equal to the number of masses, that is M1 and M2, and this mass having two inductors in the separate loop, right? And this is the voltage source. Next, step by step we have to consider what is the common path elements. So for loop concept, common path element is very important. Here common path element in these two will be just connected via the electrical elements like 1 by C and R, and corresponding to that In the second loop you will get L2, first loop L1, and corresponding to that this again K2 and B2 are there, they will be connected, right? And in case of force voltage analogy, one of the most important things is that when there will be certain say normally this storage elements which is spring and this damping elements, dampers are connected in mechanical network like parallel. So this will be in case of electrical network, that will be connected like in series, right? This is the one of the most important observations you have to make. And in case of force current analogy, what we have learned is that in corresponding to mechanical network, it was very easy to find out the mechanical network. And in case of mechanical network, if this spring and damper are in parallel, that means the corresponding electrical elements are in parallel. But in case of this force voltage analogy, only thing is that if these two are like parallel, it's looking like parallel, that means these two elements in electrical network will be replaced by corresponding electrical elements in series, right? Here these are series and these are series, and these two masses are into different loops, L1 and L2 get. So this is all about the construction of the electrical network for the corresponding mechanical network. Okay, in the next lecture um, uh, we will be discussing about the concept of block diagram, and how to reduce the defined block diagrams. That means the defined block diagram reduction techniques, and subsequent analysis for signal flow graph and all these things. Okay, thank you.